So problem says each current produces a B field on the red closed path right here, and this path is a length S, right? Evaluate the line integral BDS, right? Closed line integral. So on paper, right, if you were trying to like do this problem where it's like there's all these wires, and for this like small ds, right, they're gonna you have to use this nasty Biot-Savart law to find that, and you're gonna integrate that. Ampere told us that hey, this line integral actually ends up being mu times the I enclosed. So that's Ampere's law. The line integral b ds equals, and I really should use my vector notation, equals mu times the I enclosed. So once you know that, you're just solving for mu I enclosed. And hey, we know all the currents, right, enclosing this path. It's actually not that bad of a problem. Just a couple notes. You might be tempted. So first of all, well, what's going to be negative and what's going to be positive, right? Because we have the some current going into the page, some current going out. So remember that, like, let's say for a point right here, like, I don't know, point right here, you can use your right hand rule to kind of figure out that, okay, current going in, direction this way, so my B field is pointing this way. If this was going out of the page, so boom, boom, wait, this is hard to do. If this was going out of the page like so, you could see your B field would be in the opposite way. So you have to kind of assign a direction, right? Some of it's going to be like into the page could be positive, out of the page would be negative. And the reason is because I showed that if currents are going in opposite directions, their B field, like at a certain point produced, is going to be in the opposite direction. Some has to be minus, some has to be negative. So I'm going to assign that out of the page is positive and into the page is negative. Doesn't really matter like what you show there, just make that clear. So mu naught. So you might be tempted to just be like, okay, well, if out of the page is positive, out of the page is positive, positive 1 amps, positive 2 amps, minus 3 amps, right? So I enclosed, but it's actually a bit of a trick question because some of them are not actually enclosed by that loop. So this 6 amp current, for example, if you traced it here, you could see this actually leads out of the loop, right? If something's enclosed in a loop, like this loop right here, it's not going to be able to leave that loop, right? But, and for example, in this case, if I were to draw it like that, and I drew my thing, you could see you can draw a path out of the loop. Same thing here, this 6 amp current actually can get out of the loop there. So it's not going to be the I enclosed. So we can just not think about that. So this is kind of an annoying problem in that sense. I can save you the trouble. This 4 amp, wait, I think the rest of them are actually inside the loop. No, they're not. No, they're not. This 5 amp, you can get out of the loop there. Let's see, what else can you get out of the loop? This 3 amp can leave the loop. I'm just looking at this like little opening right here, and I'm just trying to see if you can draw. So the 3 amp for sure is not in the loop, and everything else should be in the loop. So now, then you can see, right? If I take this 4 amp, can't leave. This 2 amp has nowhere to leave. This 1 amp just leads back to the 2 amp, has nowhere to leave. So my I enclosed is going to be positive 1 amp plus positive 2 amps minus 4 amps. You get minus 1 amp times mu naught, so negative 4 pi times 10 to the negative 7th Tesla meters. So hopefully this kind of shows how you can use Ampere's law to make really crazy problems like this a little bit easier. Thank you for watching. Quick, short little video.